friends, you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. This channel provides basics of finite element analysis and computer-aided mechanical engineering design and analysis using CAD-related software. Let's get started.
Hello friends, you can see here the complete assembly of an air conditioning system. It's consisting of 6 different parts: compressor, condenser, collector, this is dryer, this is expander, and finally it is going to the evaporator. First one is known as compressor. From here, vapor refrigerant is passing at high pressure and temperature to the condenser, and at the condenser its phase is changed from gaseous stage to liquid stage. A huge amount of heat is lost, and the heat is lost in the form of latent heat. Actually, it is a constant pressure and constant temperature process, but the output temperature of this condenser is dependent on a lot of other factors. One of the factors is ambient temperature and also mass flow rate of this refrigerant. So here in this case we are planning to have 3 different analysis. First analysis will be from the compressor to the condenser. Here in this case, high pressure high temperature gaseous refrigerant will be transferred to the condenser, where it will be converted to liquid. And in the second analysis, the liquid refrigerant will be passing from the collector to the expander through the dryer, and finally from the expander to the evaporator. Again, in the last analysis, it will be passing from the evaporator to the compressor. Again, this is the complete cycle for this air conditioning system. All the parts will be explained separately while doing a specific analysis. In the first case, we will go for analysis using the first and second one, that means from compressor to the condenser. We know that in case of compressor, it is a constant pressure and constant temperature process. Let us close this one and we'll go for our first analysis from the compressor to the condenser. So this is our condenser. It is made up of copper tubes of inner diameter 14 mm and a thickness of 1 mm, and the fins are made up of aluminum of thickness 1 mm. At the end of this one, we have provided one fan to force air at a rate of 30 meters per second. Here we have provided some strainers to keep the aluminum fins close together. This is one strainer and this is another strainer. This is the inlet of the refrigerant and this one is the outlet. Okay, so what we are planning is, from this inlet we will force refrigerant at a high temperature and pressure, and finally through these fins it will extract huge amount of heat, and finally it will come to the exit end at a lower temperature, and throughout this process it will lose this temperature but pressure will be constant. Okay, now to see the flow particles inside these fins and these tubes, better to make this model completely transparent. Okay, let us make the model transparent. This is the transparent model. Now we're ready for our simulation or analysis. It will be done with the flow simulation, and for starting this flow simulation we have to create an environment that can be done with the wizard itself. Starting with wizard and keeping the name of the project as project 6, and unit system we are considering SI. Pressure will keep as megapascal and temperature will keep as degree centigrade. Next, this one will be an external analysis, and definitely we have to take heat conduction in solids and gravity will be involved. You can see here the direction of gravity will be y. So along y component it will be minus 9.81 meter per second square, and along z direction it will be 0. Next, gases, we're considering air for cooling, and refrigerant will be freon, that will be selected from real gases. We'll consider refrigerant R123. Next, we are considering copper for the tubes containing freon as the default material, and this aluminum fence will be provided during application of boundary conditions. Default values of roughness parameters we are considering. The next, thermodynamic parameters, temperature will be 20 degrees centigrade, and solid parameters will be definitely 20 degrees centigrade again. Concentration, so inside these copper tubes we will force freon at a high pressure and temperature, so concentration of freon will be 100%. That means its concentration is 1, and we will force air from outside as a coolant, so initial concentration of air will be 0. And one thing, air will be flowing from this side, and direction of air we can see Z. We will force air at a rate of 30 meters per second in the Z direction. So what we have to do is we have to change the coordinate system as Z, and we have to force air at a rate of 30 meters per second. Finish it. Done. Now you can see our computational domain is being ready. As it is an external analysis, we got a huge volume of computational domain, which is not good, because more the volume, more will be time for these calculations. Always we should try to minimize this volume to have minimum time for these iterations. So let us edit this domain. The computational domain is ready. You can check. Now we have to provide fluid subdomains, so we can hide this domain part. In our analysis we are having two types of fluids, one will be freon and another will be air, so two different domains are required. First domain will be these freons, so we have to locate that domain. So for better selection of domains, it is always suggested to have a segmented view of this model along these pipes, so we can cut it along the front plane and drag it as per our requirement to see that it should pass through the pipes. We have to select fluid subdomains, insert fluid subdomain, from this location at a pressure of 0.2 megapascal and temperature will be 70 degrees centigrade. So here we have to select refrigerant only, and pressure we are considering 0.2 megapascal. And temperature will be 70 degrees centigrade. We have to select that location from the inlet of this condenser. We have to provide vaporized refrigerant at a pressure of 0.2 megapascal and temperature 70 degrees centigrade. Now you can see that domain. This is the domain for this refrigerant. Now one thing is very important to explain here, that the temperature of exit location of this refrigerant is dependent on a lot of parameters. One parameter is ambient temperature and also mass flow rate of this freon. I have already conducted one parametric study with different mass flow rates of this refrigerant. I have seen that at different mass flow rate we are having different temperatures. We'll see in this case the freon gas will change its phase from gaseous stage to liquid, and we know that boiling point of freon is 27.8 degrees centigrade. Therefore As it will be converted from gaseous stage to liquid stage, definitely we're expecting a temperature of the liquid refrigerant at the exit end less than 27 degrees centigrade, and pressure will be almost same. Pressure will be near about 0.2 megapascal we're expecting, right? So this is the fluid subdomain for refrigerant. Now we'll select another fluid subdomain for this air that will be forced from this fan from this side to the front side of this fins. Next one, we have to select the fluid subdomain of air that will be forced from this fan at a rate of 30 meter per second. So another fluid subdomain we are considering, fluid subdomain, insert fluid subdomain. It will be only air, and its temperature and pressure will be equal to atmospheric pressure and temperature. So as it is 20 degrees centigrade, let us select that location of fluid subdomain of air. This is the fluid subdomain of air. Now one thing, if we cut this one, we can see that the domain of this refrigerant is different, right? Okay, done. Next one, we have to apply material, right? So we can have a complete view of our model. This is our completed model. Solid material, insert solid material, and the tubes should be made up of copper. We are selecting the copper tubes. Predefined metals, it will be copper. Now let us select that tubes. All the tubes are selected with copper material. Grid check. Next one, we have to select these aluminum fins. So again, solid materials, insert solid material, predefined alloys. We are selecting aluminum 6061 alloys. For selecting this one, let us select all the components. Now from this we have to deselect the pipes. Pipe is deselected. Now all the materials are made up of aluminum 6061 alloys. Selected. Next one, we have to apply boundary conditions. So again, for applying boundary conditions, we can have a segmented view of this model. When check boundary conditions, insert boundary condition. Inlet mass flow rate, let us consider mass flow rate as 0.1 kg per second, and thermodynamic parameters we are selecting 70 degrees centigrade and 0.2 megapascal for this refrigerant. Substance concentration, it will be 100% freon. So freon's concentration is 1 and no air will be there, so its concentration is 0. Now we have to select the location of this freon. For better selection, let us make this one a little bigger. Selected. Green check. So first boundary condition is applied. Now we have to apply the second one. That means atmospheric pressure and temperature at the exit location. Now you can see here, actually we have provided the lead at this location, and this portion is for assembly, and this one was connected with the collector, and finally from the collector to the dryer and expander. Now we are applying the second boundary condition. Insert boundary condition. It will be environmental pressure or atmospheric pressure at this location. For better selection, we can have a zoomed view of this one. Let's select this part. Green check. So we have applied two boundary conditions. can see the complete view of our model. Next one, we have to apply fan at this backward position, and that will force air at a rate of 30 meters per second. So fan to be provided. You can provide fan from here, conditions, fan. We are selecting external inlet fan, predefined, axial fan. Different types of fans are available. We'll select JMC products, and here in this case we'll try to have more diameters. Let us select the maximum diameter available in this case. In this case we are having maximum 32 mm diameter. You can see the specification of this one is 92 32 12 m. That means length and breadth of the fan is 92 mm and 32 mm is diameter and 12 mm battery voltage. We have to select that location, and air will be forcing out from here at a rate of 30 meters per second, and pressure and temperature at this location is equal to atmospheric pressure and 10 to 20 degrees centigrade temperature. Selected, grain check. You can see the arrows by which air will be forcing out from this location to the fence, right? So all the boundary conditions have been applied properly. Next one, we have to select some goals. Can have lot of goals, but our main aim is to have the temperature and pressure at the exit location. So we'll select mainly two surface goals. Insert surface goals. To have the goals, better to have a segmented view of this model again. We'll cut the model along the front plane. Grid check. Goals. Insert surface goal. And we're planning to have two different goals. Average temperature of fluid and average total pressure at the exit location. So we're selecting that location. Selected, green check. So both the goals have been defined. Now you can see the complete view of the model. So our model is ready for running. Let us run this simulation. The solver window has started already running. Let the iterations move on. Whenever it is finished, we'll see the results and go for further analysis. And the solver window has finished its iterations. You can see the results right now. Let us see the results from cut plots. Insert cut plots. You're going to see the pressure, temperature, etc. from the front plane. Again, you can see these things from right plane also. Initially, you want to see temperature of fluid across the front plane. So we'll change this one from pressure to temperature of fluid across the front plane. Green check. This is the temperature cut plot along front plane. Let us see this one in the form of animation. That will be a better one for push. Cut plot 1. Play. You can see here at the top side, the pressure and temperature of fan is high. Red color indicating high pressure and temperature. At this point, temperature is 70 degrees at the entry point. And as it is approaching towards the end of this pipe, its temperature is reducing. At the end, its temperature is 24 degrees centigrade. As we expected this one to be below 27 degrees centigrade. And also we can see another thing like some kind of flow of air is visible as our fan is forcing air at a rate of 30 meters per second. Now we'll do one thing. We'll see this cut plot across right plane. Cut plot 1, clear and hide this part. We'll see this thing from right plane. Cut plots, insert. Now we'll select the right plane and we're going to see temperature of fluid across the right plane. Grain check. From this one we can understand in better way. Better to see this one from side view. Now we can play this part. Cut plot 2. Let's play. You can see the pressure and temperature at the top side. It is very high. It is in the range of 70 degrees centigrade temperature, and as it is approaching towards the end, its temperature is reducing. It is in the range of 19 to 24 degrees centigrade. So we can say that the vaporized refrigerant was condensed to liquid refrigerant using this condenser. And in this case we can see the pressure. Let us see the pressure distribution. We can see pressure distribution along the right plane. Initially, while entering the pipes, pressure was very high. It is in the range of 0.36 megapascal. Though we supplied pressure at the entry location at 0.2 megapascal. Let us run this cut plot from right plane. It is showing that pressure at the beginning was very high, and as it is approaching downwards, pressure is a little bit reducing, and you can see here at the exit location pressure is 0.2 megapascal, and our input pressure was also 0.2 megapascal. That means it was a constant pressure process. You can see. Okay, so let us close this part. Clear and hide. Next, we want to see the fluid dynamics of these freon particles, and that can be done using flow trajectories. Let us see the flow trajectories of this one. Let the numbers be 60, and we want to see in the form of arrows only instead of pipes. It will show the dynamics of these freon particles throughout these copper tubes, and by the same time it will show how it is cooling by the application of forced air supplied by the fan. Particle study is running right now. It will take some time for getting all this data. Now you can see the dynamics of these freon particles. You can play this. Path of freon particles, it is clearly visible. So clear and hide this part. Finally, we want to see our results from the goal plots. Insert goal plots. And we decided 2 goals. We want to see both the goals. Select all, show. It is showing all the results. First one is the average pressure at the exit level of the copper tubes. It is showing 0.22 megapascal at the exit end, and average temperature at the exit end is 24.44 megapascal. That is approximately 24 megapascal. We told already at the beginning that boiling point of freon is 27.8 degrees centigrade. So we achieved almost near about boiling point temperature of freon. That is, it has started changing its phase from vapor condition to liquid. We want to see all these things again in the form of graphs also. from the history. Let us see these things. First graph is telling that the average pressure at the inlet was 0.2 megapascal. Within 100 numbers of iterations, it went up to 0.23 megapascal, and finally it has come down. After 100 iterations, it has maintained a constant pressure of 0.22 megapascal. That is, it is maintaining a constant pressure process. Similarly, for the second graph, we can see that initial temperature was 70 degrees centigrade, and after 550 numbers of iterations, it has come down to 24 degrees centigrade. Okay, so we can close it right now. This is all about our today's analysis of condenser. Next analysis will be from the collector to the expander through the dryer. In that case, we'll consider the output of this one as the input of the next analysis. So if you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.